We are on the Sea of Marmara, the exact spot where the massive continents of Europe and Asia meet. It's a vital, beautiful waterway packed with cargo ships on the surface, but dive underneath and you'll find a geographical nightmare lying on the seafloor. Deep underwater, two massive slabs of the Earth's crust are violently grinding past each other. This isn't just a minor crack in the dirt, it's a colossal geological fault. A massive complex system of continuous fractures that has been accumulating a devastating amount of energy for decades. We call it the Great North Anatolian Fault. All this energy has to be unleashed someday. And when it happens, it's going to hit one of the most densely populated areas on our planet. Scientists are now in active monitoring mode, especially when it comes to Turkey. This country is sitting on the Anatolian Plate, a small bite of the Earth's crust. Nowadays, it's being literally smashed by the Arabian Plate from the south and the Eurasian Plate from the north. Because it's being squeezed so hard, the only direction it can move is west toward the Aegean Sea, and it actually does this at a speed of about 1 inch per year. In geological terms, that's a high-speed, violent movement. Millions of tons of solid rock grinding against each other deep underground day and night without a single break? Not the best thing to experience. All this endless moving, cracking, and squeezing is what creates the North Anatolian Fault, a 930-mile-long fault line that acts almost exactly like the infamous San Andreas Fault. Yet the difference is striking. While the San Andreas mostly skirts the outer edges of Californian megacities or runs through less dense regions, the fault in Turkey is running right under major industrial hubs and heavily populated urban centers. In February 2023, the smaller sister of it, the East Anatolian Fault, showed us how dangerous this tectonic setup can be. It generated the most catastrophic earthquake recorded in Turkey in over 60 years. A brutal 7.8 monster hit and a 7.5 shockwave followed right behind it just hours later. The release of energy was so violent that the ground literally moved by almost 10 feet in some places. Entire cities were leveled and the physical map of the region permanently shifted. Now the worst part, it wasn't even the grand finale. There's no way to stop that energy packed inside the North Anatolian Faults. Look at the old data and you'll see it acts like clockwork, a bit like a line of falling dominoes. Scientists have been tracking every sequence of earthquakes in this region for nearly a century. The whole chain reaction started in 1939 with the catastrophic Erzincan earthquake. A massive magnitude 7.8 struck eastern Turkey. It didn't simply release the energy, but also transferred this tectonic stress into the next section of the fault. Dominoes started falling. Other fault rupture happened in 1942, 1943, and 1944. It went west and struck again in 1957 and 1967. Year by year, the epicenters of these massive earthquakes moved in a straight line toward the Sea of Marmara. The last major impact was the Izmit earthquake in 1999. A magnitude 7.6 tremor struck east of Istanbul and lasted for 37 terrifying seconds. Suddenly, the chain reaction took a break, but the tectonic stress was still there, simply transferred to the next section of the fault, under the Sea of Marmara, where the last major earthquake took place in 1766. Nobody had seismographs back then, but historical records and old journals describe it as a scene of unimaginable horror. Now, modern science tells us exactly why it was so devastating. Scientists are calling it a seismic gap, basically a dangerously quiet zone that hasn't ruptured yet. Back then, 260 years ago, a massive quake destroyed a huge part of Istanbul and generated a tsunami that crashed into the city's ports. After this tragedy, it didn't happen again on this scale, but we have to remember that the Anatolian Plate has never stopped moving west, an inch a year. Let's do some quick math. That land should have moved by over 19 feet by now. But because those rocks are locked together, they haven't moved an inch. We are looking at a massive backlog of tectonic tension. It simply has to snap finally, and it won't make a regular shake. It will likely rapidly release 2.5 centuries of accumulated tectonic energy, right at the doorstep of Europe and Asia. The target is the city of Istanbul once again. We should call it a supercity because this global mega hub is home to an astonishing 15 million people. It accounts for nearly 30% of Turkey's entire economic output. What about the infrastructure? We're talking about 1 million buildings, and an estimated 90,000 of those are at high risk of total collapse in the event of a magnitude 7.5 earthquake. Nowadays, the city has very strict laws for modern buildings. But plenty of urban areas had been built before those regulations were enforced. To make matters worse, many coastal neighborhoods are built on soft, waterlogged soil that acts like a liquid during extreme shaking, multiplying the danger for the residents. Buildings could just sink into quicksand. And there's more. The seafloor of the Marmara Sea isn't flat. There are 3 massive deep underwater holes separated by vast ridges. Why is it important? A stronger earthquake in this area will probably trigger a massive submarine landslide. Plenty of mud and rock collapsing down those underwater canyons would instantly displace massive amounts of water. This would trigger a tsunami, not as tall as mega tsunamis in the open Pacific Ocean, but still highly dangerous. It's estimated that with a 10-foot wall of water, it will be extremely dangerous for this densely populated area. Scientists also claim that it could hit the coastline within 10 minutes. There would be almost no time for a mass evacuation. Here comes modern technology. Engineers are fully aware that this geographical clock is ticking and are fighting back. Essentially, infrastructure is being heavily retrofitted. Also, the mighty bridges crossing the Bosphorus Strait have been reinforced with seismic dampers to absorb extreme shocks. One of the world's largest seismically isolated buildings is located at Sabiha Gökçen International Airport in Istanbul. It's sitting on massive bearings made out of rubber and steel. The absolute art of engineering is the Marmara Tunnel, a massive railway tube that runs directly under the Bosphorus Strait, physically connecting the European and Asian continents underwater. It was built right next to an active fault line, so it had to be designed with flexible earthquake-proof joints. If a megaquake hits and the continents shift, the tunnel will bend and flex like a giant snake rather than snapping in half. Another concern of scientists is the economic aftershock of this rupture. It may affect the entire globe, as the Bosphorus Strait is one of the world's most critical maritime choke points. Every single year, nearly 50,000 ships pass through this narrow waterway, carrying everything that is crucial for the global market: barrels of oil, agricultural goods, and so on. The price of energy and food would go crazy if this shipping line collapses. To buy some precious time, scientists have installed an advanced early warning network on the seafloor of the Marmara Sea. Fiber optic cables and seismometers are constantly listening to the fault. But because the epicenter is located so incredibly close to the city, even this multi-million-dollar system won't give residents enough time to escape. At best, it will provide a maximum of 5 to 7 seconds of warning before the destructive waves hit the city. 5 seconds to shut down gas lines, halt the trains, and brace for the impact. Of course, all this effort won't protect the whole city. Only a fraction will survive. The undeniable conclusion is that the migration of earthquakes isn't just a theory, but a well-documented geographical reality. Scientists estimate that there is a 65% probability of a magnitude 7 or greater earthquake striking the Sea of Marmara region before the year 2030. Now we can see that the rupture in this area isn't just a possibility. It is coming, and it is migrating directly toward the collision point of two continents.
So here's the famous Grand Canyon in Arizona, a gigantic crack in the ground of incredible beauty and grandeur. Now, imagine it dozens of miles longer and lying at the bottom of the ocean. In fact, you don't have to imagine it, because you can see this scene in real life. A massive crack in the ocean floor lies about 620 miles west of Portugal. This mysterious rift is called the King's Trough Complex. It's a broad system of parallel trenches and basins descending into the dark depths of the Earth's crust. All of this awe-inspiring beauty stretches for about 310 miles. The deepest part of the system is known as Peak Deep. It's located at the eastern end and is one of the deepest places in the Atlantic Ocean. The Bermuda Triangle, the Mariana Trench, and other places, surrounded by mysteries, secrets, and legends, may fade into the background compared to the King's Trough Complex. There are no frightening stories or records of vanished ships here, but just imagine it. At the bottom of the Atlantic Ocean, in icy waters where almost no light reaches, lies a giant unexplored rift. What's down there? What kind of creatures might be found? Perhaps there are remains of sunken ships. We are unlikely to find out anytime soon because reaching it is extremely difficult due to the immense pressure. For now, the only thing scientists truly understand is the origin of this underwater canyon. But first, let's look at how similar formations appear on the surface. The Grand Canyon, for example, was formed by a river. Meandering slowly over millions of years, it carved through the region, washing away and grinding down sedimentary rock. So here's the question. Do you think something similar happened to the floor of the Atlantic? Of course, there are no rivers there, but what about underwater currents? Could they have created such a giant, dark fissure reaching deep into the Earth's crust? Well, in fact, no. The origin of the King's Trough Complex is connected to the movement of tectonic plates and the thermal activity beneath them. But how did scientists determine the cause? Well, the rift lies deep underwater in complete darkness. That wasn't a problem for researchers. They sailed to the site on a research vessel and used a powerful sonar system to create a detailed map of the area. After obtaining a clear picture of the terrain, they selectively retrieved volcanic rock samples from different parts of the trench using a chain bag dredge. After that, they delivered the samples to laboratories for chemical analysis. All of this data helped scientists discover that between 37 and 24 million years ago, this part of the North Atlantic temporarily became a boundary zone between the European and African tectonic plates. Tectonic plates are enormous slabs of rock that cover the Earth's crust like a planetary-scale mosaic. They move, collide, overlap, and push away from one another. The King's Trough Complex formed during a period when the Earth's crust was splitting apart because of the movement of tectonic plates. It pulled away from east to west, resembling a giant zipper being undone. Now, in addition, scientists found evidence that the crust in this area was subjected to intense heating, rising from deep within the planet. Although researchers don't know exactly what occurred, it's likely that hot material, known as a mantle plume, rose toward the surface. All of these events deformed and fractured the Earth's crust, leaving us with what could be called an underwater Grand Canyon. But why are we interested in this at all? What does knowledge of events that happened tens of millions of years ago give us? Well, scientists now better understand how processes deep within the mantle can influence the movement of tectonic plates. This major research also provides insight into the geological evolution of the Atlantic seafloor. All of it helps humanity better understand similar processes taking place today. For example, near the Azores, another giant system of trenches known as the Tercera Rift is forming right now. What will happen next to this rift? Is such an event dangerous for people? One of the reasons scientists conduct these studies is to answer questions like these. It's unknown what secrets may still be hidden within that underwater fracture. But let's return to land and our beloved Grand Canyon. Even though it is famous worldwide, there are things inside this canyon that may surprise you. The Grand Canyon is ancient, yet it continues to change. Rock erosion happens slowly, but with each passing year, the canyon grows deeper and its shape evolves. Now, if you plan to visit the Grand Canyon, prepare for unpredictable weather. The canyon has its own climate, which can differ from the surrounding region. Because of the dramatic elevation changes, temperatures constantly shift. Snow may fall along the rim, while not far below, people inside the canyon enjoy warm sunshine. Walk a little farther and higher, and you might find yourself in the rain. Take shelter lower down, and you could end up surrounded by fog. So plan your route carefully and check forecasts from official weather services. There's both good and bad news for archaeologists. In the Grand Canyon, you can find ancient fossils of marine creatures more than 1 billion years old. In its caves, there are traces of land mammals dating back 10,000 years. The bad news is there are no dinosaurs here. The canyon most likely formed after those ancient reptiles became extinct. Now, one thing that may surprise you during a hike through the Grand Canyon is Supai Village, with a population of about 200 people. It's located at the base of the canyon within the Havasupai Indian Reservation. It's the most remote settlement in the continental U.S. and the only place in the country where mail is still delivered by pack mule. There are no roads leading to the village, and if you want to visit it, you'll need to prepare for a challenging hike along steep slopes under the blazing sun. Beyond its fascinating natural features, the Grand Canyon also has things that are almost fantastical and eerie, at least according to rumors and legends. For example, there's a hotel room known as the Grand Canyon Cavern Suite inside the canyon, deep within one of the caves. At a depth of 220 feet, guests find a luxurious room with all the comforts and, according to some accounts, something unsettling. Some visitors have reported stones moving inside the room, frightening dancing shadows, strange sounds, and movements near the bed where they were sleeping. You might also hear many local legends about spirits and monsters that inhabit the canyon. Of course, these are just stories, but some truly tragic events have taken place here. The canyon has become a grave for many people. Over time, around 800 people, according to official records, have passed away here. There were accidents, mysterious incidents, and real tragedies. For example, in 1956, 2 airplanes collided in the sky above the canyon. And that was far from the only case. So be careful when you come here. Stay away from the cliffs and keep close to your group. There is also a theory that ancient advanced civilizations once lived in the Grand Canyon. These rumors began in 1909 when a local newspaper published a major article claiming that 2 archaeologists from the Smithsonian Institution had discovered a secret tunnel filled with Egyptian artifacts and mummies. The Grand Canyon and ancient Egypt? How could that be possible, considering the vast distance between them? Soon after the article was published, the Smithsonian Institution issued a denial. No archaeologist from the institution had conducted such research, and certainly none had found Egyptian artifacts. Many believe the newspaper had published a hoax, although some suggest the institution deliberately concealed information about hidden discoveries. In any case, the story seems highly unlikely. Now, even though you know all this and want to see something similar yet different, you should travel to Tibet, where the Yarlung Zangpo Canyon is located. It is 2 miles deeper and 30 miles longer than the Grand Canyon. There, you would also see many fascinating things, but that's a topic far too large and deserves another video.
Australia feels like the safest place on Earth, geologically speaking. No megavolcanoes, no massive fault lines slicing cities in half, no constant earthquake alerts. It looks solid and unbreakable, but according to a brand new global stress map of Earth's crust, Australia is one of the most internally stressed pieces of land on the entire planet. It's not shaking or cracking yet, but it's quietly storing energy like a bent ruler about to snap. To understand why this is such a big deal, imagine Earth's crust like a giant jigsaw puzzle made of moving slabs called tectonic plates. These plates float on softer rock below and push, pull, or grind against each other. Where plates meet, earthquakes and volcanoes make sense. But stress doesn't just stay at the edges, it travels. It builds up inside plates too, like pressure spreading through frozen ice when you squeeze it. Scientists mapped over 100,000 real stress measurements from oil wells, rock tests, and earthquakes to see where Earth is being squeezed the hardest right now. When they laid all the data together, the map lit up like a warning sign, and Australia stood out. This shocked scientists because Australia sits far away from plate boundaries, which usually means stability. But instead of relaxing, the Australian continent gets squeezed from multiple directions by nearby plates, especially the Pacific and Eurasian ones. The stress doesn't release easily, so it piles up inside the crust, and then nothing moves. Until suddenly everything does. One of the strangest discoveries showed up in places like the Bowen Basin, where stress directions twist and rotate underground. That's bad news because unpredictable stress behaves like glass about to shatter. These rotating stress fields make it nearly impossible to say when or where cracks could form. It could be years away or tomorrow. And human activity makes it even riskier. Drilling deep into the crust for geothermal energy or injecting fluids underground can nudge these stressed zones just enough to trigger fault movement. This doesn't mean Australia is about to split in half next week. But it does mean the idea of geologically safe might be outdated. Scientists now think Australia could eventually fracture internally and form new fault systems where none existed before. What makes the new stress map different from older models is that it doesn't just explain past earthquakes, it helps identify future risk zones before anything breaks. Countries can use this data to decide where drilling is safer, where tunnels shouldn't go, and where infrastructure needs reinforcement. But even with all this data, we still can't predict the exact moment Earth will snap. Stress maps tell us where the tension is. They don't tell us when it gives up. But this idea of continents quietly tearing themselves apart isn't just theory. Africa gives us the clearest real-world example. It's slowly unzipping itself. So slowly that no human will ever wake up and see a new ocean where land used to be, but fast enough that scientists can actually measure it happening right now. Deep beneath East Africa, the ground stretches, thins, and pulls apart as if the continent is taking a deep breath and never fully exhaling. And over millions of years, that stretch could turn into an ocean. This whole process centers on something called the East African Rift System, or EARS for short. Think of it like a giant tear running through the continent, thousands of miles long, cutting through countries like Ethiopia, Kenya, Tanzania, and Mozambique. It's one of the biggest rift zones on Earth. A rift zone is exactly what it sounds like, a place where the planet's crust is being pulled apart instead of squeezed together. And Africa just happens to have one of the most dramatic examples anywhere on the planet. What's really happening is that Africa isn't one solid plate anymore. It's splitting into two massive chunks, the Nubian plate to the west and the Somalian plate to the east. These two plates are drifting away from each other at a speed that sounds laughable, just less than an inch per year. That's about the speed your fingernails grow. But give that process millions of years and suddenly continents don't look so permanent anymore. In 2018, photos of a giant split in Kenya went viral across the internet. Headlines screamed that Africa was splitting in half right now. It looked dramatic, but that moment didn't mean Africa suddenly broke overnight. That rupture was more like a surface ripple, a small local sign of a much bigger process that's been going on for around 25 million years. And if we could travel in time to 5 or 10 million years from now, we would probably see the crust thin enough for seawater to rush in. When or if that happens, East Africa would slowly peel away from the rest of the continent, and a brand new ocean basin would form between the two plates. Africa would lose its eastern shoulder, and maps of the world would need a serious update. As strange as that sounds, it's actually totally normal for Earth. The planet never stops reshaping itself. It just works on a timeline so slow that our brains struggle to process it. The continents we know today feel ancient and permanent, but they're basically temporary arrangements. About 138 million years ago, South America and Africa were locked together like puzzle pieces. You can still see it if you look at their coastlines. They match almost perfectly. East Africa drifting away will just be the next chapter in that story. Australia's story could follow a different path, but the physics are similar. Stress builds, rock resists, then the rock fails. And stress doesn't care about borders, cities, or how calm the surface looks. That's why scientists are so concerned about something called SH-max, the direction of maximum horizontal stress. In simple terms, it tells us which way the Earth is squeezing the hardest underground. If that squeezing lines up with existing fractures, earthquakes become more likely. If it cuts across old faults, new ones can form. Turkey is another place where the stress map practically screams danger. The country sits where Arabian, Eurasian, and African tectonic plates collide. There's also a smaller Anatolian plate on which Turkey is located, and which gets squeezed westward like toothpaste, grinding against massive faults. The stress map shows SH-max pointing in directions that load these faults perfectly. Now, researchers looked at ancient lava flows near one of Turkey's faults and realized they weren't random. Lava sheets once flowed smoothly across the land, cooled into solid rock, and then got pulled apart over time, like a snapped chocolate bar. That gave scientists a rare, clear snapshot of how continents deform from the inside out. To date the lava, the team used microscopic zircon crystals trapped inside it. These crystals work like natural stopwatches. They trap helium created by radioactive decay, and by measuring that helium, scientists can tell when the lava erupted and cooled. When they combine that with satellite images and remote sensing, the scientists managed to see Earth's slow-motion movements. The Tuzgolu Fault stretches more than 120 miles and is so massive that you can spot it from space. For years, scientists assumed it behaved like many of Turkey's dangerous faults, where land slides sideways past itself. But this new research flipped that idea on its head. The fault isn't sliding, it's slowly ripping open. The land on either side moves away from each other at less than an inch per year. That sounds tiny, but then again, over thousands or millions of years, that motion adds up to continents literally thinning and breaking. And since the fault sits where three massive tectonic plates meet, this matters way beyond Turkey. All this once again reminds us that continents don't just collide or slide. Sometimes they stretch until they snap. And places that look calm on the surface might already be under invisible strain, inch by inch, year after year, rewriting the map long before anyone feels the shake. Right now, as you read this, two colossal slabs of rock are locked against each other beneath the streets of Oakland, California. It sounds like nothing to an unprepared person, but the problem is that they're pressing harder with every passing year, storing up energy like a spring that's been coiling for more than 150 years. Roughly 30 feet below the sidewalks where people walk their dogs and grab their morning coffee, a geological clock has already run out. And scientists now know with uncomfortable precision exactly what happens when it finally lets go. This is the story of the Hayward Fault, one of the most dangerous strips of land in the United States, and the extraordinary computer simulations that are finally revealing the full picture of what the next big earthquake will do to millions of people. Let's start with the fault itself, because the Hayward Fault is not some distant geological curiosity hiding far out in the wilderness. It runs for roughly 74 miles right through the heart of California's East Bay, directly under neighborhoods, schools, hospitals, and highways. in cities like Oakland and Berkeley. More than 2 million people live or work along its path. And it is, by scientific consensus, overdue. The last time the Hayward Fault produced a major rupture was in 1868. That earthquake, estimated at magnitude 7, was devastating by the standards of the time. It flattened buildings across Hayward and sent shockwaves all the way into San Francisco. But here is what makes today's situation so much more serious. The fault's average cycle between major earthquakes is around 140 years. We are now more than 150 years past that last rupture. The clock has not just run out, it ran out over a decade ago. The numbers from the United States Geological Survey make this concrete. There is roughly a 1 in 3 chance of a magnitude 6.7 or larger earthquake on this fault within the next 30 years. But the Hayward Fault doesn't operate in isolation. When scientists factor in connected faults in the region, including the nearby Rogers Creek Fault to the north, the probability of a major rupture somewhere in the system climbs to 72% by the year 2043. That is not a distant hypothetical. That is a near certainty within most people's lifetimes. So what exactly happens when it breaks? For decades, the honest answer was, we're not entirely sure. General earthquake models existed, but the Bay Area's geology is complex, a patchwork of hard rock, soft sediment, deep basins, and hill formations. And predicting how seismic waves travel through that maze was beyond the computing power available. That changed recently. Researchers at Lawrence Livermore National Laboratory and Lawrence Berkeley National Laboratory used some of the most powerful supercomputers on Earth to run 50 separate simulations of a magnitude 7 earthquake on the Hayward Fault. Each simulation varied the details, where exactly the rupture starts, how the slip spreads across the fault surface, how fast the break travels. The result is not one prediction, but a rich, detailed map of possibilities, showing not just where shaking will occur, but how intense it will be, how long it will last, and why certain neighborhoods face dramatically higher risks than others. What they found should reshape how every Bay Area resident thinks about where they live. The most important takeaway from these simulations is this: the ground does not shake equally. Location matters enormously, and the differences are not subtle. Take the Eastern Hills, places like Orinda and Moraga. These communities sit on layers of softer sedimentary rock, and that geology acts like an amplifier. In a major Hayward Fault earthquake, shaking in these areas could be up to 50% more intense than in western neighborhoods sitting on solid bedrock. That is not a rounding error. That's the difference between a building that survives and one that doesn't. And then there's Livermore Valley, which faces a different but equally serious problem. The valley sits in a geological basin, and seismic waves behave strangely inside basins. They bounce around, trapped between the basin walls, unable to escape. Instead of the shaking lasting the usual few seconds, simulations show it could continue for more than 2 minutes in Livermore. 2 full minutes of sustained, violent shaking. For pipelines, warehouses, and industrial infrastructure, that duration is potentially catastrophic. In Oakland and Berkeley, right on top of the fault line itself, the main danger comes for what scientists call directivity pulses. When a pulse ruptures, the break doesn't happen all at once. It races along the fault, and in doing so, it flings concentrated bursts of energy forward like a wave from a moving source. Communities directly in the path of that forward momentum get hit with sharp, powerful pulses that are particularly destructive to tall buildings. Skyscrapers and high-rises in these cities face the highest risk from this effect, with ground accelerations that can reach the equivalent of the full force of gravity. Enough to overwhelm structures that were not built with this specific threat in mind. Meanwhile, on the western side of the Bay Area, underlain by the hard Franciscan bedrock, things look noticeably different. Ground acceleration there could be 20 to 50% lower than in the highest risk zones. San Francisco itself will certainly feel the earthquake, but distance and solid geology provide meaningful protection. This does not mean Western neighborhoods are safe. It means they are safer, relatively speaking. To understand why geology creates such stark differences, it helps to think about how seismic waves actually move. When a fault ruptures, it sends waves radiating outward in all directions, much like dropping a stone into a pond. But unlike water, the ground is not uniform. Hard bedrock transmits those waves quickly and efficiently, so energy passes through without lingering. Soft sediment, by contrast, slows the waves down, compresses them, and forces them to grow taller and more violent. The same way ocean waves rear up and crash when they hit shallow water near the shore. The Bay Area sits on an extraordinary variety of ground materials, which is precisely why two neighborhoods just a few miles apart can experience the same earthquake in dramatically different ways. The simulations capture this complexity in finer detail than any previous model, and the results make clear that geology is not just a background detail, it's the single biggest factor determining who gets hurt and who walks away. What makes these simulations genuinely groundbreaking is that they don't just produce abstract data, they produce actionable intelligence. Engineers can already use these results. For skyscrapers in Oakland and Berkeley, the pulse wave risk means buildings need reinforcement specifically designed to absorb those sharp, sudden jolts rather than the slower, rolling motion of distant earthquakes. In Livermore, foundations for new construction must account for extended shaking durations, not just peak intensity. In the eastern hills, slope stability becomes a critical concern. Steep hillside homes face elevated landslide risk when shaking amplifies. For public infrastructure, Bay Area Rapid Transit, BART, and the region's freeway systems are being prioritized for retrofitting based on the directivity cone maps and simulations produced. The fault doesn't just threaten buildings, it threatens the transportation networks people will desperately need after a major event. And for ordinary residents, the implications are personal and practical. Securing heavy furniture, water heaters, and bookcases reduces injury risk. Early warning apps can provide seconds of notice before shaking arrives, enough time to drop, cover, and hold on. Emergency supplies for at least 3 days are not excessive preparation. For a region this exposed, they are basic common sense. The science of earthquake prediction is moving fast. These simulations are already being extended to the San Andreas Fault, modeling potential magnitude 7.5 or larger events. Higher resolution subsurface mapping will push the models to even finer detail. But the Hayward Fault simulation already tells us something profound. We do not need to be helpless in the face of this threat. The ground beneath the Bay Area is not a mystery anymore. We know where the danger concentrates. We know why some neighborhoods will shake harder, why some valleys will shake longer, and why some buildings face risks that others don't. The question is no longer whether this earthquake is coming. The question is whether we will be ready when it does.
Here you are in a park, enjoying a normal day, when suddenly dark, muddy clouds appear above you. But this doesn't last minutes or hours. It goes on for weeks, and everything around you is slowly starving for sunlight. This is exactly what happens on the ocean floor, and scientists gave it a name. They call it marine dark waves. You may have heard of underwater heat waves. This is when the ocean gets way too hot and stays this way for weeks or months. This happens because the ocean acts like a giant sponge for the planet. When the atmosphere traps heat from the sun, the ocean soaks it up. Sometimes warm currents get trapped in one spot, like hot water swirling in a bathtub, slowly cooking everything trapped inside. The heat wipes out stuff that can't move, like corals or seagrass, while fish either flee to cooler waters or struggle as oxygen levels drop. Because these plants and reefs sit at the base of the food web, the damage ripples through the entire ocean ecosystem. Marine heat waves are a huge problem. However, dark waves are almost equally bad, but in a completely different way. A marine dark wave is obviously not about the heat. It's about light suddenly disappearing where it's supposed to exist. If we can imagine the ocean like a giant glass building, where sunlight normally pours through windows and lights up every floor, dark waves would be like someone filling that building with thick smoke. It happens when the water gets clogged with a thick, swirling soup of turbid matter. The water itself becomes a light-eating fog. Basically, mud, sand, algae, and all kinds of microscopic organic junk get stirred up and suspended in the water, scattering and absorbing sunlight before it can reach the seafloor. When it gets thick enough, the seafloor disappears into darkness. This starves any life at the bottom that depends on the sun for food. And the strange thing is, we're not talking about a deep dark ocean miles below where sunlight never reaches anyway. All of this happens near the coast, right in the shallow parts where underwater plants need the sun to survive. What makes dark waves especially tricky is how easy they are to miss. From the surface, everything can look normal, even to satellites. You can park a boat on top of a dark wave and still not notice anything weird. That's why this phenomenon went largely unnoticed and wasn't properly studied until recently. To properly catch whatever was turning off lights at the seafloor, scientists started cross-referencing data like detectives. They had to dig through archives and build a kind of time machine out of old data. They gathered 16 years of continuous light readings taken directly from the bottom of the Santa Barbara Channel. Then they matched that with more than 20 years of satellite-based light data from the coast of New Zealand. They essentially rewound the security camera footage of the ocean for the last 2 decades to see what they had missed. With all that data combined, researchers found a specific event in New Zealand where the seafloor received almost no usable sunlight for 64 days. Imagine if the sun set on the 1st of November and didn't rise again until after New Year's Day. If that happened on land, it would be a disaster for anything that needs sunlight to grow. Think about your houseplants. If you shoved a fern in a closet for a week, it would probably look a bit sad, but it'd bounce back. But if you left it in there for 2 months, it'd turn yellow and slowly wither away. On a larger scale, if a forest lost the sun for 64 days, the undergrowth would rot. That would cause deer and other animals to run out of food, and the whole food chain would get shaky. It's a similar biology for the underwater world, because it also needs the sun. Down there, instead of pine trees and grass, you have giant kelp forests and seagrass meadows. They're like the oxygen gas stations of the sea. They take sunlight and turn it into fuel for the entire ecosystem. When a long dark wave hits, it drains their batteries until nothing grows back. The same thing happens to kelp. It starts to deteriorate. The fish that munch on it go hungry, and suddenly, a vibrant underwater city turns into an underwater ghost town. Marine dark waves don't just affect underwater plants. They can even affect those higher up on the food chains. We often assume that sea animals hunt by scent, but they actually depend heavily on sunlight. Many sharks and large fish rely on sunlight in contrast to hunt. They're built to spot dark shapes moving against brighter water, especially when sunlight filters down through clear water. Think of it like watching shadows move behind a white curtain. Even in low light, that contrast pops. But a marine dark wave wipes that away. The water turns cloudy, the background goes dark, and the silhouettes simply disappear. Sharks still have other senses, like picking up tiny electrical signals from nearby animals, but that only works when they're close. They're not blind, but it feels like trying to hunt in a room filled with thick smoke. You can still feel things close by, but anything further away is invisible. Apex predators don't pass away easily, but their hunting efficiency drops, which changes who eats, who escapes, and who goes hungry. That confusion stretches all the way to the docks. Fishing towns depend on marine life behaving predictably. If fish can't feed, they move on. That leaves nets empty and boats coming back light. Boat captains can read a weather radar to dodge a storm, but there is no forecast for the ocean running out of light. It also creates a headache for professionals working below the surface. Sonar helps, but divers and research teams still use their eyes. A dark wave alters how light travels through the water, turning a familiar worksite into a murky haze. Navigation becomes a guess. Surveys fail. It is a new stress factor, one the experts never planned for because, until recently, it wasn't even recognized. We've talked about how dark waves happen, but what triggers them? Well, most of the time, it's something loud and chaotic on the surface. Events like major storms and floods, rivers exploding with runoff. When huge storms hit land, they tear soil, mud, and organic matter off the landscape and flush it straight out into the ocean. All that material spreads out into massive underwater plumes that can turn clear coastal water into chocolate milk almost overnight. Scientists can spot surface sediment plumes clearly, but they can't always tell you how dark it gets down on the seafloor. Coastlines darken as sediment clouds expand. The sun might be shining above, but the water is so full of particles that no light can get through. Coastal currents often trap this murky water in place, so the darkness lingers long after the rain stops. That's why dark waves often show up after extreme weather. This creates a deceptive gap. The storm passes, and we assume the recovery has started. But underwater, the water column is still loaded with light-blocking debris. What looks like a return to normal on the surface is actually weeks of extended gloom below. As storms get stronger, we see more of these dark wave situations showing up. The ocean is getting slammed with intense mud and organic plume events that are causing this. Heavy rain leads to more floods and landslides, turning rivers into speedy conveyor belts that dump tons of soil and debris into the sea. Even after the storm passes, waves and currents can keep that cloudy mess swirling around, making the water stay murky for a while, like a shaken snow globe. So, what's next? Scientists are finally taking marine dark waves seriously instead of brushing them off as some spooky ocean myth. Now that we've got a name for these lights-out events and a way to track them, the next step is simple. We need to set up more light sensors in key spots. We also need to figure out how dark waves relate to storms, runoff, and algae blooms. Finally, we need to pinpoint the moment when ecosystems can't bounce back anymore. Basically, we're creating an underwater sunlight weather report because it turns out the ocean just doesn't have storms and heat waves. Sometimes it has its own kind of eclipse.
A leftover chunk of an ancient tectonic plate is on the move beneath North America, right under the southern part of the Cascadia subduction zone. This isn't some harmless debris. It's a real slab of Earth that never fully disappeared. And because it's still sliding around down there, it could be adding a whole new layer of stress to a region that already has a reputation for massive earthquakes. This story started with weird signals showing up in seismic data. It's basically Earth's X-ray. Scientists send waves through the ground and watch how they bounce back. These waves started acting wrong beneath the Pacific Ocean off the western US coast. Instead of smooth, predictable patterns, researchers saw a giant, coherent block deep below the seabed, moving differently from everything around it. It didn't look like a landslide, didn't look like loose debris, and didn't behave like normal ocean crust. That's when someone dared to ask the question out loud. What if this is something much older and much bigger than we thought? Some researchers seriously wondered if this could be a remnant of a lost continent, maybe a forgotten shard of Pangaea, the supercontinent that once stitched almost all land together. Technically, it's not fully impossible. Continents break, sink, stretch, and vanish over millions of years. This fragment was enormous, solid, and oddly shaped, which made it hard to classify. It didn't fit into the usual categories scientists use to explain underwater structures. Then came the slow, careful reality check. Scientists brought in more data, better models, and deeper analysis. They measured the age of the rock, studied how seismic waves bent through it, and compared its motion to known plate movements. That's when the picture shifted. This wasn't a lost continent at all. It was something just as dramatic, but far more dangerous. A massive leftover fragment of an ancient tectonic plate. This fragment turned out to be a survivor from the Farallon Plate. This ancient plate once dominated the Pacific, but got mostly swallowed as it slid beneath North America millions of years ago. Most of it vanished into Earth's mantle, but not all of it went quietly. This chunk survived like a splinter that never fully sank. Researchers named it the Pioneer Fragment, and the name fits because it's charting territory we didn't even know existed. And this fragment isn't just drifting harmlessly, it's moving horizontally beneath North America, which is weird and dangerous in geological terms. Normally, plates collide or slide past each other in predictable ways. This fragment behaves like a wrench jammed into a machine that already runs under insane pressure. The West Coast already balances on fault lines that store stress like stretched rubber bands. Add a giant moving rock slab underneath, and suddenly the system becomes harder to predict, harder to model, and much harder to feel safe about. The region where this fragment lurks already scares geologists. You've got the San Andreas Fault, famous for snapping without warning. You've got the Cascadia Subduction Zone, capable of producing earthquakes so powerful they rewrite coastlines. Now, scientists realize there's a hidden player deep beneath the ocean floor, something satellites can't see, and scientists can't directly observe. This fragment doesn't follow clean, predictable rules. Think of it like stacking dominoes on a table that's already shaking. It moves slowly, but in geology, slow movements still means unstoppable force. And when that built-up energy is finally released, it won't care about evacuation plans or building codes. There's also a timing problem that nobody likes to talk about. Geological processes don't run on human clocks. Stress can build for centuries and snap in seconds. The Pioneer Fragment might trigger something tomorrow, or it might sit quietly until generations forget about it. That uncertainty makes planning brutally hard. Cities like Los Angeles, San Francisco, and Seattle already prepare for known earthquake threats. Now, scientists must consider a system that can amplify disasters in ways nobody has practiced for. So, scientists now race to update models, improve seismic imaging, and understand how this fragment interacts with nearby faults. They know they can't stop earthquakes. All they can do is reduce surprises. And it's also clear that sometimes the most dangerous threats aren't coming from space, but sliding quietly beneath the sea. Another recent ancient landmass discovery wasn't nearly as dramatic, but super important for science. It started as a sand dredging operation off the coast of Indonesia, but then archaeologists found more than 6,000 fossil fragments from a lost submerged ice age landmass. Among them were 140,000-year-old Homo erectus remains. That single find forced scientists to rethink how early humans lived, moved, and interacted across Southeast Asia. For a long time, researchers assumed the Homo erectus population on Java lived cut off from everyone else. But those dredged-up fossils proved that Java wasn't an island. It sat right in the middle of a massive Ice Age landmass called Sundaland. Indonesia, Malaysia, Borneo, Thailand, and Vietnam are all connected into one enormous landscape. But we now call islands like Java, Sumatra, Borneo, and Bali were linked together through huge river systems that probably rivaled the Amazon. Dense forests stretched across the land. Giant animals roamed freely, and wide coastal plains existed where ocean waves sit today. And Homo erectus didn't just survive there, they thrived. And no, this wasn't a snowy wasteland, unlike how we mostly imagine the Ice Age. Sea levels dropped more than 400 feet because so much water was locked up in glaciers. When that happened, massive chunks of the ocean floor rose above the surface like natural stepping stones. Early humans didn't need boats. They could literally walk from mainland Southeast Asia to places we now think of as isolated islands. They moved while tracking animals, exploring open land, and following food sources. It worked like a giant prehistoric highway system. When the Ice Age ended, glaciers melted like forgotten ice cream cones on a hot sidewalk. Sea levels rose, slowly at first, then fast. Rivers overflowed, coastlines vanished. Entire human landscapes slipped beneath the waves. Over thousands of years, Sundaland drowned, and the people who lived there had to adapt or move to higher ground. Now, archaeologists piece together this lost world bone by bone, artifact by artifact. Every new discovery pulled from the seabed brings us closer to rewriting the story of early human migration. Studying submerged landmasses and lost continents is a work that takes years. In 2017, scientists made an announcement that changed this universal truth that there are 7 continents in the world. The discovery of Zealandia. Zealandia's story ties straight back to Gondwana, the ancient supercontinent that started breaking apart hundreds of millions of years ago. Around 80 million years ago, Zealandia split off too. But while Australia stayed high and Antarctica mostly held its ground, Zealandia slowly sank. Only a small chunk stayed above sea level, even though many geologists argue it still qualifies as a full continent. That little bit you can actually see today is mostly New Zealand, along with a few nearby islands that also belong to Zealandia. By the end of 2025, scientists had finished mapping the northern 2/3 of it, covering nearly 2 million square miles of submerged land. Researchers dredged rock samples all the way from the Fairway Ridge to the Coral Sea. They pulled up all kinds of material: pebbly and cobbly sandstone, fine-grained sandstone, mudstone, bioclastic limestone, and even basaltic lava. And these rocks came from wildly different time periods. When researchers lined all this up, they saw something big. The internal stretching from both Zealandia and West Antarctica caused the crust to thin and crack in a way similar to subduction. That cracking let ocean water rush in and helped form the Tasman Sea. A few million years later, Antarctica continued pulling away, stretching Zealandia's crust even more until it thinned so much that sinking became inevitable. This directly challenges the older idea that Zealandia broke apart mainly through sideways strike-slip motion. The team also thinks the direction of that stretching shifted by as much as 65 degrees, which likely helped the continental crust thin out way more than expected. Monaco seems powerful. Wealthy people and Instagram influencers walking outside the casino, posh cars pulling up to elite residences, and a tiny cup of coffee that costs more than a kilogram of freshly roasted beans you could enjoy at Café de Paris. Over 700 under Grimaldis, the same family. This place seems invincible, but this luxury veneer is more fragile than you think. This seemingly unsinkable power could be destroyed within minutes by something far more powerful than money: nature. Well, it's not actually only about Monaco. The French Riviera is pretty long, and the danger hangs over not just France, but Italy too, especially the Liguria region in the northwest. I know you may be watching this video from somewhere far away, and these places may not ring a bell to you, but you've definitely seen them before, at least as a screensaver once in your life. Well, this beauty could one day be buried under an extremely powerful tsunami. And if the word tsunami gives you Japanese vibes, we can make it à la française and call it radomare or maremoto in Italian. It's true that when most people hear the word tsunami, they imagine giant waves crashing into the coast of Japan, Indonesia, and other countries bordering the Pacific. For decades, the Mediterranean Sea seemed different, smaller, calmer, and far removed from the world's most famous tsunami disasters. But scientists and international organizations are now warning that this perception is misleading. A tsunami in the Mediterranean is not a distant possibility. According to experts, it's something that will almost certainly happen again within the next few decades. Yes, again. The French Riviera has already experienced more than 20 documented tsunamis, the most recent one taking place in October 1979. And strangely enough, it was not caused by nature alone. It was more like an unlucky chain of events. At the time, Nice Airport was undergoing a massive expansion project. Authorities wanted to extend the runway farther into the sea and build a new harbor area. Was it really necessary? Honestly, probably yes. If you look at the map, you'll realize Nice is basically the only major airport serving this whole part of the Riviera. Cannes does have an airport, sure, but it mainly serves private jets. Monaco only accepts helicopters, so technically it doesn't even have an airport. The two closest large commercial airports are in Marseille, about 200 kilometers away, and Genoa in Italy, around 190 kilometers away. Turin is technically another option, but driving there means crossing difficult alpine roads. And the train takes more than 4 hours. So yes, Nice desperately needed that expansion. But during the construction works, a massive underwater landslide was suddenly triggered beneath the sea. Huge amounts of mud and rock collapsed downward like an avalanche underwater. This movement displaced enormous amounts of water and created tsunami waves that struck around 60 miles of coastline. In Antibes, the waves reached more than 11 feet high. The disaster took up to 23 human lives and caused flooding, as well as major property damage. And that's the scary part about tsunamis in this region. They do not always need giant Hollywood-style earthquakes. Sometimes, a collapse beneath the sea is enough. The Mediterranean is smaller and more enclosed than the Pacific Ocean, which means waves can travel toward the coast very quickly. In some places, people may only have minutes to react. So, could something like this happen again? Did the locals learn their lesson? Well, construction along the Riviera never really stops. Nice is currently going through major urban transformation projects as part of a push toward modernization and sustainability. While the historic center and the Promenade des Anglais remain mostly untouched, there are still significant construction zones around the port, Nice West, and the airport area. Nobody is saying current construction will directly trigger a tsunami, but UNESCO is still issuing serious warnings. Their monitoring programs and scientific assessments indicate that there is effectively a 100% chance that the Mediterranean will experience at least 3 tsunamis over 1 meter high within roughly the next 30 years. And 3 feet may not sound very large at first, but tsunami waves behave very differently from normal beach waves. They carry enormous amounts of fast-moving water and energy. Even relatively small tsunamis can flood streets, damage buildings, overturn vehicles, and place thousands of people in danger. This very part of the Mediterranean is unique. It has everything packed together: sea, mountains, and dense coastal cities. In some places, like Menton, the geography is truly one of a kind. Menton is shielded from cold northern winds by the Alps and the Prealps. This traps warm Mediterranean air, giving the town more than 300 days of sunshine every year, and some of the warmest winters on the Côte d'Azur. The city itself is tiny. You could literally walk across it in under 2 hours, and the buildings are pushed very close to the coastline. At the same time, the population density is pretty high, and huge numbers of tourists arrive every year for the Lemon Festival and all things lemon-related. Now, imagine a place this tiny hit by a tsunami. Horrible, right? The tsunami danger specifically in Menton comes from 3 main things: nearby earthquake faults, steep underwater terrain, and crowded beaches during summer. And the key issue is that the danger is not far away. It's literally sitting right offshore. Beneath the sea near Menton lies a giant crack in the earth called the North Ligurian Fault System. It sits only about 12 to 18 miles offshore. Deep underground, 2 giant pieces of the Earth, the African plate and the European plate, are constantly pushing against each other. Most of the time, the movement is slow and invisible, but sometimes pressure builds up until the ground suddenly jerks upward. When this happens beneath the sea, the water above gets pushed upward too, almost like someone slamming a hand into a bathtub. That sudden movement can create a tsunami within minutes. This already happened in 1887 during a large earthquake in the Ligurian Sea. The earthquake affected cities across Italy and France, including Genoa, Savona, Nice, Menton, and even Cannes. People reported something terrifying. First, the sea suddenly pulled backward, exposing parts of the beach that are normally underwater. Then the water rushed back toward the coast as a wave. Earthquakes near Menton also triggered underwater landslides. Huge amounts of sand and mud can suddenly collapse downhill beneath the sea, like giant avalanches underwater. When all that material moves at once, it pushes water aside and can generate dangerous waves. Even earthquakes happening far away in North Africa can sometimes send tsunami waves across the Mediterranean toward the French coast. What makes this even more dangerous is how calm the sea usually looks. Menton's Sea has very small tides, so the water often appears peaceful and harmless. Because of this, many visitors never imagined that a tsunami could happen there. And during summer, the beaches become packed with families and tourists. If a large wave arrived suddenly, evacuation would become extremely difficult. Now, let's rewind for a second to the Ligurian Sea, because the name may have sounded a little strange earlier. Yes, it does exist. Technically, it's part of the Mediterranean Sea, but many people refer to it separately because of its geography. It sits between northwestern Italy, the French Riviera, and islands like Corsica and Elba. And this entire area is particularly vulnerable. The African and European tectonic plates are colliding right beneath this region. That collision created the beautiful mountains everyone admires today. But it also causes earthquakes, which means many famous cities in this region sit directly inside an active geological zone. Genoa, Pisa, Florence, Nice, Antibes, Menton, and of course, glamorous Monaco, right on the coast. The same force that created the Riviera's beauty is also what makes it dangerous. And because so many towns here are squeezed tightly between mountains and the sea, there's very little room to escape if a tsunami suddenly arrives. That is exactly why scientists and emergency agencies are becoming increasingly worried about this coastline. Most people think of continents as permanent. Europe is Europe. North America is North America. Their borders feel ancient, pretty much fixed and untouchable. But there is one country on Earth where that illusion breaks apart in real time. Now, I've got a question for you. Which country sits on two continents? If you're a geography guru, you may name countries like Kazakhstan, which is mostly in Asia but does have a small part in Europe. Or maybe Egypt, which stretches from Africa into Asia across the Sinai Peninsula, famously using the Suez Canal as a continental boundary. But I'm talking about Iceland here. You have every right to say, wait, Iceland is in Europe, period. And culturally and politically, you'd be absolutely right. But geologically, that's a completely different story. You see, Iceland is a country where the planet is physically pulling itself open. You can stand with one foot in North America and the other in Europe. Not symbolically. The ground beneath you literally belongs to two entirely different tectonic plates drifting away from each other every single year. And the separation is still happening right now. Every year, the gap grows by roughly 1 inch. That may sound tiny, almost meaningless, but that same slow movement has already reshaped the surface of the Earth. Over tens of millions of years, it opened the entire Atlantic Ocean. It separated land masses that once sat side by side on a single supercontinent. The same force stretching Iceland today is the reason New York and London now sit thousands of miles apart. So no, Iceland is not simply a country with volcanoes. It is one of the only places on Earth where you can literally watch continental drift happening with your own eyes. And it sounds simple when you first hear it. A country between two continents. Cool geography fact. But once you really understand what's happening there, Iceland becomes one of the strangest places on the planet. Because beneath the Atlantic Ocean lies something enormous, the Mid-Atlantic Ridge. This thing is massive, but over 90% of it is hidden underwater, which is why most people have never heard of it. And Iceland is one of the very few places where part of that underwater mountain range rises above sea level. That alone makes the country geologically extraordinary. The Mid-Atlantic Ridge marks the boundary between two gigantic tectonic plates, the North American Plate and the Eurasian Plate. And these plates are not stationary slabs of rock. They move constantly. driven by slow currents of superheated material deep inside Earth's mantle. At Iceland, those plates are diverging, pulling apart, separating inch by inch, just like a bag of chips that you tear open. Normally, this process happens invisibly beneath the Atlantic Ocean. Nobody actually sees continents moving apart because it usually happens under miles of water. But Iceland is different. Iceland sits directly on top of the mid-Atlantic ridge itself, which means you can literally walk across one of the most important geological boundaries on the planet. And probably the best place to see this is Thingvellir National Park in southwestern Iceland. At first glance, the place almost looks unreal. The landscape is ripped apart by enormous cracks and canyons, with jagged black lava fields stretching in every direction. Massive rock walls rise straight out of the earth like the remains of some collapsed ancient world. But these are not just old geological scars frozen in time. These fractures are active. They exist because North America and Europe are still pulling away from each other beneath your feet right now. And most visitors walking through the area have absolutely no idea they are literally standing between continents. In some places, the water filling these fissures is so unbelievably clear that you can see deep into the submerged fault lines below. And the landscape itself is still changing. Over the last 10,000 years, the Thingvellir Rift Valley widened by roughly 230 feet and sank around 130 feet as the tectonic plates kept separating. So this is not some ancient event that happened millions of years ago and then stopped. The process is still happening today, which naturally raises a pretty obvious question. If Iceland sits directly between two tectonic plates moving away from each other, why hasn't the island already split in half? And the answer is what makes Iceland even stranger. As the plates slowly pull apart, pressure deep underground drops, allowing molten rock from Earth's mantle to rise upward and fill the gap. Once that magma reaches the surface, it cools into completely new crust. So Iceland is basically being torn apart and rebuilt at the exact same time. That balance is what keeps the island together. This entire process is known as seafloor spreading, and it is one of the main forces shaping the surface of our planet. As tectonic plates drift apart, magma rises from deep inside the Earth, cools into volcanic rock, and creates entirely new crust. Without this process, the Atlantic Ocean itself would not even exist. Around 60 million years ago, the Atlantic was dramatically smaller than it is today. North America and Europe sat much closer together as leftovers of the ancient supercontinent Pangaea. Then the mid-Atlantic ridge slowly began forcing them apart. It didn't happen through giant apocalyptic explosions or one massive catastrophic event. It happened thanks to simple, relentless movement measured in inches per year. And honestly, that's the part human brains struggle to understand. An inch per year sounds harmless because human lives are short, but geological forces do not care about human timescales. They never stop, and over millions of years, tiny movements become oceans. The Atlantic Ocean itself is basically proof of that, and Iceland sits directly on the fault line where that expansion is still happening today. The island's volcanic activity is part of the exact same process. Iceland is one of the most volcanically active places on Earth, with more than 15 volcanoes erupting there during the last century alone. And this is not random bad luck. Iceland occupies an incredibly unusual geological position because it sits not only on the mid-Atlantic ridge, but also directly above something called a mantle plume. Basically, a massive column of superheated rock rising from deep inside the planet. You can think of it like a giant underground blowtorch constantly feeding magma into Iceland's crust and fueling volcanoes across the island. And the result is a landscape that feels unfinished in the best possible way. Lava fields still warm from recent eruptions, steam vents hissing straight out of the ground, geysers blasting boiling water into freezing air. So while in many countries, geological history feels ancient and distant, and in Iceland, geology feels pretty much alive, Some eruptions there are so large they actually create entirely new land. Fresh lava cools into black volcanic rock, slowly expanding Iceland outward. So even though the tectonic plates are trying to pull the island apart, volcanic activity keeps adding new material back in. Iceland is basically patching itself faster than it can fully split open. Now, that does not mean Iceland is stable in the normal sense. Earthquakes are still common. Cracks can still open unexpectedly. Entire regions rise and sink as magma moves beneath the surface. Scientists constantly monitor the island using GPS stations, satellites, and seismic instruments, because Iceland functions almost like a live laboratory for plate tectonics. And honestly, there are very few places on Earth where researchers can observe continental drift this directly, and even fewer where ordinary people can physically experience it themselves. There's even a location on Iceland's Reykjanes Peninsula called the Bridge Between Continents. It's a small footbridge spanning a fissure created by the separating tectonic plates, and tourists casually walk across it in seconds, crossing from the North American plate to the Eurasian plate. Not gonna lie, that sounds almost fake when you first hear it. Like, a literal bridge between continents? Seriously? But the deeper reality behind it is even stranger. But it all makes sense once you realize continents are not permanent objects. They're fragments of crust floating atop a dynamic planet. They merge, split apart, collide, sink, and reform over unimaginable spans of time.